So let's have a look at how this type of question works, because this is a prime example. In fact, you could get one like this on your unit or even final exam. Okay, it's exactly the type of question I would ask. So in this question, is this a work energy theorem question or is this a conservation of energy question? It's a conservation of energy question. And the way we can tell that is, were you given force? Were you given any distance? Okay, then it can't be a work energy theorem question, and we were never told work. The word work doesn't appear anywhere in this question. All right? What we are told is that something is sliding down a hill. Okay? If it's sliding down a hill, then the only force doing anything is the force of gravity. Okay? So all that's going to happen then is the mechanical energy is going to stay the same. The mechanical energy near the top and the mechanical energy near the bottom are going to be equal. How much of that mechanical energy is potential and kinetic is going to be different, but their sum is going to be the same number. Is everybody okay with that idea? Okay? That's the law of conservation of mechanical energy. All right? So in the first position up here, this would be our initial point. Right? The person is 30 meters above the bottom, vertically. Right? And they are moving at 1.5 meters per second. Later, they're moving at 7.5 meters per second and are still not quite at the bottom of the hill. What we're being asked to calculate is how high above the bottom of the hill are they now? Okay, everybody all right with what we're looking for in the setup here? Okay, so here's how we go about solving a question like this. Once we've recognized it's not a work energy theorem question, then we know that we need to start it out like this. As a law of conservation of energy question. Okay? And just to give you a bit of a tip, the contexts that I typically use for a conservation of energy question are roller coasters and people sledding down hills. Okay? Or like a bobsled or a luge or something like that. Okay? All right, so we got the initial mechanical energy equals the final mechanical energy. Did we learn the other day how to calculate mechanical energy? Okay, so what two things do I put together? To get mechanical energy, I add two things. What are they?
Potential and kinetic.
The potential and the kinetic. So that means then that on this side, I would say the initial potential plus the initial kinetic, that would give me my initial mechanical, equals the same thing on the other side, but final. So my final potential plus my final kinetic. Right? So this is the patterned part that we've already done. We did a couple like this yesterday. Now, the next kind of part of this pattern is figuring out if I actually have all of those. The examples we did yesterday, we didn't have all of those. Okay? Basically, we were dropping something and figuring out how fast it would be going at the bottom where the height would be 0. That's not the case here. Okay? So at the beginning, near the top of the hill, they're 30 meters above the bottom. So do they have potential energy initial? Okay. They're moving at 1.5 meters per second. Do they have kinetic energy initial? Right. They got both kinds. So neither one of those is 0. I can't cross either of them off. Now, when we're talking about this point down here, they're asking us to calculate the height. That would imply that it's probably not 0. Would you agree? Okay. So we do have some final potential energy, most likely. Okay. And they're moving at 7.5 meters per second, so do they have kinetic energy? All right, so that means none of those are 0. That means it can't cancel any of them. Okay, everyone all right with that so far? All right, so they want me to calculate the final height. Which one of these terms is final height going to be part of? EPF, right? Height goes with potential energy. We're looking for the final height, so that's part of the final potential energy. So before I do anything else, like put in a bunch of formulas with even more variables, I want to isolate this. How do I get EPF by itself?
Subtract.
Right, subtract which one?
The EKF.
The EKF, right. I'm adding EKF to EPF, so I'm going to subtract EKF over to the other side. So that'll leave me with this. Initial potential plus initial kinetic minus the final kinetic equals the final potential. Okay. this point, I want to put in all the formulas. Okay? So the formula for potential energy is M times G times H. And in this case, it'll be the initial height, so H and I, right? Plus 1/2 mv squared. And in this case, it'll be the initial V. Okay. Minus 1/2 mvf squared. Okay, so that's the formula for the final kinetic energy. And then lastly, on this side, m times g times h. Fine. Okay, so now everything, in terms of formulas at least, is in our equation. Are we still saying the same thing we said the line above? We are. We've just expanded it out now to include all the little parts. Okay? Is it easier to manipulate it before I do that? It is. Like to move that EPF over before I have all the M's and G's and H's is way easier to do it then. Okay? All right, I'm trying to solve for HF. So what do I need to move next? MG, how would I move it? Divide it over to the other side, right? I'm multiplying those three things together. So to move it over, I would do this. Okay, and go on from there. Okay, am I ready to plug in numbers? I've isolated what I'm looking for, right? So now I'm ready to plug numbers in. There's nothing else to do now. I'm solving for HF, which is what the question asked me to do. So all I have to do now is plug in all these numbers. Okay, so the mass, we were told, is 70 kilograms. Now I'm going to show you a little thing after this, but I actually don't need that number. Okay, I'm going to put it in just because it's in the formula, but I'm going to show you a bit later that we actually don't need it. Okay, so we'll put it in. So 70 kilograms times 9.81, so times G, times our initial height, which was 30 meters, plus 1/2 times 70 kilograms, the mass, times 1.5 squared. That was our initial speed. Sorry, it's up here where we can't see it. Okay, 1.5 minus 1/2 times 70 times 7.5 squared. That's our final. Okay, so it's there. And then I divide all of that by 70 times 9.81 m times g. So saying the same thing on this line here that I said on the line above. That's going to equal my final height. All right, so if I punch all that into my calculator, 70 times 9.81 times 30 plus 0.5 times 70 times 1.5 squared minus 0.5 times 70 times 7.5 squared. Okay, divide that by 70 times 9.81. Okay, so they haven't gone very far. Okay, they're still 27.2 meters above the bottom of the hill. Because it actually doesn't take very long for you to pick up speed on a frictionless hill. Not that one of those exists, but it really wouldn't. Okay, if it was frictionless, take you very long to pick up speed. Okay. Okay, did we have to do all that much here? Right, like we wrote EI equals EF, then we expanded it to this. Then we manipulated for EP, then we put in the formulas, manipulated, plugged in numbers, and solved. Okay, that's the pattern. It's always going to be that same pattern for a conservation of energy question. And the only things you'll be asked to solve for in a question like this are height, like we just did, or speed. Okay, and we'll do one with speed so you see what that looks like as well. But they're very, very patterned. Okay, talking about not needing the mass. Why, even though I put mass in there, would I actually not need that 70 kilograms?
Because you're dividing by 70, so it would just cancel out.
Well, actually, because I've got pluses and minuses on the top, it doesn't actually mathematically cancel because of that division. But when I was looking at it this way here, actually, sorry, before I manipulated, okay, when it was just in a straight line, was m part of every term? So if I multiply every term by the same number, does that number have any effect on the equation at all? It doesn't. Mathematically, it's kind of like when you do factoring. I know that's the F word, right? Factoring, but and maybe it's like kicking up a trauma response for you, but if it's in every single term, I can factor it out. It doesn't matter anymore if every term is multiplied by it. You can choose. You can leave it in, you'll get the same number, okay? Or you can take it out, and I'll prove to you, I'll get the same number, okay? 9.81 times 30 plus 0.5 times 1.5 squared, okay? Minus 0.5 times 7.5 squared, okay? Divided by 9.81. So I took out all the 70s. I get exactly the same number because I multiplied every single one of those numbers by 70. So taking it out makes no difference at all. But totally up to you. Okay? You can leave it in if that makes you more comfortable. You can take it out if you'd like to not punch as many buttons. Okay? It makes no never mind to me. There was only one time where it messed people up, and that was my fault. I gave a unit exam where I didn't give the mass on the conservation of energy question. And then one person came up to my desk and they're like, Mr. Coderre, I think you forgot to put the mass in that question. And I was like, oh, yeah, it's 200 kilograms. And then back to their desk. Another person came up about 5 minutes later. Mr. Coderre, you think you forgot to put the mass in this question? I was like, oh, right. And I couldn't remember what mass I told the first person. So it's like, it's 700 kilograms. And the person went back to the desk, and then I see out in the class, there's like a few people's eyes that are like this, because I realized I'd just given two different masses. So then I had to stand up and say, guys, use whatever mass you want. You can use 1, you can use 250 million. It doesn't make any difference. But pick one. Okay? So it doesn't really matter. Okay, any questions on what we did there? That is a very, very typical conservation of energy question. Okay. All right, let's have a look at question number 2 here, okay, where we're talking about the kicker kicking the football. Okay, so right here on the ground at the initial point, okay, so what kind of energy does it have? The kicker's foot is just about to make contact with it. The kicker's foot is just about to make contact with it, and it's on the ground. Okay, so like, I'm sorry, I should have maybe set this up. When you start a game in football, you put the football on a tee and it just sits there, and then the person runs up and kicks it. So it's just sitting on the ground on the tee. Does it have any energy at all? No. Okay, now once the kicker kicks it and it just leaves his foot, still kind of on the ground, but now it's off the kicker's foot. It's going really fast. What kind of energy does it have? Kinetic. No potential yet because it's effectively still on the ground. Okay, now what about right here? What kind of energies or energy would it have there?
Potential.
It would have some potential. Would it have any kinetic? I think it would. It's still moving, right? Like when you kick a football, it doesn't go straight up in the air unless you kick it straight up in the air. Okay? In a football game, if you kick it straight up in the air, someone's going to run you down. Okay? So you kick it forward. Right? So it's still moving forward. It would still have both types of energy at that point. But a lot of people will say only potential because they're picturing it going straight up in the air. Okay? This is still moving forward. Okay. Yeah, that's what I'm going to do with those. I would like you guys to try question number 5. Okay. So it's a bit of work energy, so a bit of that is review. There's no, it's not until you really get to kind of F and G that things start to get a little more mathematical. Okay, I'll give you guys a little bit of time to work on number 5, and then we'll look at it together. Okay, questions about it? if I want to calculate the work done for part A, work is force times distance. Did they give me those two things? Right? They told me the force is 40 newtons and the distance is 0.1 meters. Right? So if I go 40 times 0.1, I get 4 joules. So I did 4 joules of work compressing this spring. What happens to that work? What does it become?
Potential energy in the spring.
It becomes elastic potential energy in the spring. Okay, so that requires no calculation. That's just, I understand that when I push a spring, this is what happens. Okay, if the spring is released, what will happen? Okay, Nelson?
They were released in the form of kinetic energy.
Right, it will accelerate the ball. I think they put a ball on the spring. It would accelerate the ball. In fact, it would do work on the ball because it's going to transfer its potential energy to the ball, and the ball will gain kinetic energy or mechanical energy. Calculate the energy the ball has the instant that the ball leaves the spring. This is where conservation of energy comes in. I did 4 joules worth of work. There were 4 joules of potential energy in the spring. How much kinetic energy does the ball have? 4 joules. That's all the energy that's in the system. Okay? There can't be more, there can't be less, because energy can't be created and it can't be destroyed. Okay? If I put 4 joules of energy in the spring ball system, that's all the energy the spring ball system will ever have. Okay, now for part E. Now you have to do a calculation. What kind of energy does the ball have now? Once it leaves the spring, it has what kind of energy? Okay, I put a ball in the spring, then let the spring go. It's going to shoot the ball, right? Okay, the ball's just going to go along the floor. Okay, what kind of energy will the ball have when it leaves the spring?
Kinetic.
Kinetic. Did we just say how much kinetic energy it would have? Okay, calculate the speed of the ball. We know the ball's mass, and we know how much energy it has. Give you a couple minutes to calculate the speed of the ball. All right. How much kinetic energy does the car have, or the ball? 4 joules, okay? We just said that here. Calculate the energy that it has, 4 joules. Okay, if that's its kinetic energy, and kinetic energy is 1/2 mv squared, I know this number, 4 joules, and I know this number, because the question told me what it was, 0.01 kilograms. Okay, so I can manipulate for V. I just divide both sides by half of m. So we'll have EK divided by half of m equals V squared. So if I square root that, I'll have V. So square root of 4 over 0.5 times 0.01. And if I square root that, that'll tell me the speed the ball will leave the spring at. So right, it's going to leave it at 28.3 meters per second. The car didn't go that fast. But the ball is going to, because it only has a mass of 10 grams. It's very, very small. Okay, it's probably like a small marble or something. Okay, everyone understand what we did for E? Okay, F is very similar, except now, and I'm not going to do this with the cart, we launched it vertically. Okay, if we launch it vertically, it comes off the spring, still has kinetic energy the moment it leaves the spring, but now they want to know what's the maximum height we'll go to. Okay, how much energy will it have at its maximum height? How much energy is in the system? 4 joules. How much energy will it have at its maximum height? 4 joules. Conservation of energy. Can't go anywhere. Okay? It all has to stay there. See if you can calculate its height, knowing that its energy at its maximum height is 4 joules. What kind of energy will it have there? Potential. Okay? Because what we're doing is shooting it straight up in the air. Okay? If it goes straight up in the air, at its maximum height, it stops for an instant. It only has potential there. Okay? Calculate the height. I'll give you 1 minute. It's an easy calculation. Okay, let's look at that calculation. Oh, shoot, I left the recording running. Okay, so we are looking for, okay, what the maximum height of the ball will be. Right, so that's gonna be then M times G times H. Okay, I know this number here is 4 joules. I know this number is 0.01 kilograms. I know this number is 9.81 meters per second squared. So all I have to do is isolate H. So I'll divide both sides by mg, okay, and I'll have this. The height equals 4 joules divided by 0.01 times 9.81. Okay, that'll give me the maximum height the ball will reach. All right, it's going to reach a maximum height of 41 meters. That's pretty high, but it's a pretty small ball. Okay, 4 joules can do a lot of work on a small ball. Okay, questions on that? All right, number 6 is basically the same thing we did here. Okay, we're looking for the athlete's initial vertical speed. So a 60-kilogram athlete is just going to jump vertically from the ground. So they're just going to be standing here in place. They're doing like a vertical jump test. Okay, and they're just going to bend their knees and they're going to jump as high as they can. Right, and when they do that, it's an impressive 0.91 meters off the ground vertically. Okay, so that's the maximum height they can reach. I want you to calculate how fast they were going when they left the ground. It's conservation of energy. And it's very much like what we did yesterday with the kid on the trampoline, okay, and the rock being dropped off the cliff. In fact, it's the exact opposite of the rock being dropped off the cliff. Okay? All right. Give you a couple minutes to see if you can figure that one out, and then we'll walk through it. All right, so we have a 60-kilogram athlete. So our givens are that we know the mass, 60 kilograms, okay, although it's probably not going to matter. And they are jumping from the ground. What's your height on the ground? 0. Okay, so they're jumping from the ground, so their initial height is 0 meters to a final height of 0.910 meters. Okay? How fast are they going at that final height? 0, because that's their maximum height. You slow down all the way to your maximum height. Okay? So VF is 0 meters per second. Okay? We're looking for what speed they left the ground at. That's VI. Okay? From the context of the question, that's what I get. Okay? Now, is their energy, the instant they leave the ground, the same as it is at their maximum height, their total mechanical energy? It's the same, because there's no work being done in between. Okay? Whatever energy they leave the ground with is all the energy they are going to ever have. Okay? So at their maximum height and on the ground, they have the same amount of mechanical energy. I get that from the context of the question, that this is a conservation of energy question. Okay? I know it's a conservation of energy question because also I wasn't given any forces or any distances, and there was no mention of work. Okay? Now, since it's a conservation of energy question, and this is mechanical initial and mechanical final, okay, I want to put in the formulas for mechanical energy. Okay, all right with what I wrote there? That's how we calculate mechanical energy, right? Kinetic plus potential. Are any of those 0? Which ones? So initially they're on the ground.
EKF and PI.
Right. Their initial potential is 0 because initially they're on the ground. And their final kinetic is 0 because at your maximum height, your velocity is 0. Okay? So now we're left with this. My initial kinetic equals my final potential. Okay? So that means 1/2 mv initial squared equals mgh final. Very much like the rock dropping question or the kid on the trampoline question. Okay? So I'm looking for VI. How do I get VI by itself?
Divide by half
happen to the m's?
Cancel.
Is that gonna cancel? All right, so that's gonna get me vi squared. What do I want?
Yeah.
Just vi. So that's what I'm left with. Square root of g times hf over 1/2. Okay, when I plug in my numbers, 9.81 times 0.910, that was the final height, divided by 1/2, that'll give me the speed they jumped at. Okay, so they jumped at 2.1 meters per second. Did that one follow the same pattern? Okay, as long as we learn the pattern, just like work energy theorem question, as long as we learn the pattern, we're good. They're giving it a dirty look.
Just figuring something out.
Okay, did I type something in wrong? I didn't include brackets, maybe I should have. I don't think it would have mattered for this one. Oh, I multiplied by 0.5 instead of dividing.
Yeah.
See, that's why it was good to give it a dirty look. Coder messed it up. That's better. 4.22 instead. Yeah, meters per second. Does that make people happier?
Yeah.
Okay, I'm sorry. That was my bad. Okay. Questions on that one besides Coder can't operate your calculator? Happens all the time. Okay. Well, let's. Okay, let's try this one. This is like the sledding question, except instead of looking for the final height, now we're going to look for the final speed. Okay. As soon as it doesn't come back. Okay, so here's our situation for this question. We have a 1,600 kilogram roller coaster, and it starts 50 meters above the ground, moving at 5 meters per second. A little while later, it's at this point on the track, and it's 8 meters above the bottom of the roller coaster, above the ground, and I want to know how fast it's going. Okay, it's a frictionless track. There's no forces other than gravity. Okay. It works just like the sledding question, if you want to look back at that. Okay, except instead of solving for height, we're solving for speed. All right, so we know right off the bat, there's no force, there's no distance, there's no work being done. The energy at the top of the first hill is the same as it is anywhere else on the roller coaster after that. Okay, conservation of energy. Now, mechanical energy is the sum of an object's potential and kinetic energies on both sides of the equal sign. Okay, now according to the context of this particular problem, we are initially at 50 meters above ground level, so we have initial potential. We are moving at 5 meters per second, so we do have initial kinetic. We are finishing 8 meters above the ground, so we have final potential. And we're looking for the final speed. It's definitely not 0. All right, so we have all 4 of those. We can't cancel any of them off. All right, now what I'm looking for, VF, is part of this. So I want to isolate that before I plug in the formulas. So what do I have to move? EPF. How do I do that? Subtract it over to the other side. Okay, so I'm going to have initial potential plus initial kinetic minus final potential equals final kinetic. Okay, now I can plug in my formulas. So the formula for potential, m times g times h initial, plus 1/2 mv initial squared, minus m times g times h final equals 1/2 mv final squared. All right, m is in every term. Do I need it? I don't. You can leave it in if you want, but I hate entering extra stuff. So I'm taking it down. Okay? Now, I'm trying to find VF, so what do I have to do with this 1/2? Divide it over to the other side, right? Okay, that gets me VF squared. What do I want? I just want VF, so what do I have to do with the whole thing? Square root it. Is this always coming out to basically the same thing? There's really only two ways this goes. I solve for H or I solve for V, okay? But it's the same manipulation. All right, so what we're looking at here is 9.81 times 50. That's my initial potential. Plus 1/2 times 5 squared, my initial kinetic. Minus 9.81 times 8, my final potential. Divided by 1/2. That's going to get me VF. Right, so when I'm punching all that in, I don't like putting that all in one step because there's a good chance I'll mess something up. So I do it kind of one piece at a time. 9.81 times 50. Okay, plus 0.5 times 5 squared. Minus 9.81 times 8. Divided by 1/2. Okay, and then I square root that. Okay, so I get 29.1 meters per second at that point. Now, in walking around, just kind of seeing what people had written, most people that I looked at had got most of the work right. Okay? But at some point, there was like one little thing that was missing or something wasn't punched into the calculator correctly. A question like this is going to be worth between 6 and 8 marks. Should you show your work? Yes, because there is a good chance that we mess up. I messed up on the calculator twice today, okay? And I do this all the time. So it's really easy to make a mistake on the calculator. But if you've shown me that you knew how to do it by showing all of your work, and you're just like me and you can't punch the numbers on your calculator correctly, that's okay. That only costs you 1 mark, okay? If you show me all the work, then I know you knew how to do it. Okay? So if I'm looking at this, I would give you 1 mark for your givens. I would give you 1 mark for recognizing it's a conservation of energy question. I'd probably give you 1 mark for identifying if any of these were 0 or not. Okay? I'd give you another mark for manipulating. I'd give you another mark for plugging in your numbers correctly. What are we up to there? 5 and 6 for your answer. Okay? Sometimes I get like super crazy with the marks, and I give 2 more for like various steps in between. Okay? So show your work. Right? That way, if you do make a mathematical error in your calculator, you still get 5 out of 6 or 7 out of 8. Okay? Definitely worth your while. If all you show is a number and it's wrong, you get 0. Okay? And that would suck. Okay? I would not like to see that happen for you. Okay. How are we feeling about these? They're pretty involved. Okay, like I'll give you that. The algebra, writing all that stuff out, all those steps, it's pretty involved. But it's the same involvement every single time. Okay, like to this point here, okay, it's the same every time. And then there's only 2 variations on that. You're either solving for a V or you're solving for an H. Okay, so when it comes right down to it, there's only really 2 things to practice. Solve for V or solve for H. Okay. All right, let's maybe look at, okay, we've done one like this. See if you can repeat it. Toboggan on a hill was the first question we did today. Okay, that was cool. Whole thing here yet. Okay, so the setup is this. We've got our hill, okay, got our toboggan, right? And at one point it's 30 meters above. Okay, and moving at 14 meters per second. Okay, shortly thereafter, the sled is moving at 23 meters per second. We're looking for HF in this situation, okay? The height above the ground at that point. Okay? So those are your givens, plus you weren't given the mass. So you can either choose whichever one you want or don't use it at all. Okay, give you a couple more minutes and then we'll walk through it. Okay, so for this one, there's no work being done, so we know that the mechanical energy isn't changing, and it's a conservation of mechanical energy question. All right, and we set it up, same as we always do. Initial potential plus initial kinetic equals final potential plus final kinetic. Okay, none of those are zero. We have all of those four types of energy, okay? Because we have initial potential, we have initial kinetic, we have final potential, we have final kinetic, okay? So none of them can be canceled off. What I'm looking for is HF, which is part of that term. So I'm gonna wanna isolate that term by subtracting the kinetic final over to the other side. So I have this, initial potential plus initial kinetic minus final kinetic equals final potential. Okay, now I can put in my formulas, m times g times h initial plus 1/2 mv initial squared minus 1/2 mv final squared equals m times g times h final. Since m is in every term, what can I do with it? I can cancel it off, yeah, or I can make it whatever I want. 1, 250 million, 5, it doesn't make any difference, okay, what it is. So I choose to make it nothing. Okay. All right, now that I've got that, I want to solve for HF. So I'm going to divide both sides by G. That'll leave me with HF, and now I just need to plug in my numbers. All right, so we will have 9.81 times 30 plus 1/2 times 14 squared minus 1/2 times 23 squared. Okay, so that's my initial potential, initial kinetic, final kinetic. Okay, and then I divide that by G, 9.81. That will give me my final height. Whoops. Okay, and then subtract 0.5 times 3 squared. And then divide that by 9.81. Okay, so the final height is going to be 13 meters. Everybody all right with that one? Okay, we're going to work on that again tomorrow a little bit. Okay, you are going to have a quiz tomorrow. Be some questions like this, but probably a little bit easier. Okay, but it'll be on the same kind of mode. So tomorrow, conservation of energy. Friday, we'll see how we're doing for conservation of energy. And if we're doing well after tomorrow, we might move right on to efficiency. Okay, next week we'll have a lab. I think I have it scheduled for Wednesday. Okay, and your unit exam is Thursday. Next week, tomorrow. Okay, so unit exam is Thursday of next week. I will post the unit exam review package maybe today or tomorrow, so you can start having a look at it. We'll do a formal unit exam review probably on Monday.
The unit exam is on Wednesday.
Oh, sorry, is it Wednesday? Sorry,
Yeah.
the 31st. Okay, then I have the lab scheduled for Tuesday. I'm still messed up with missing Monday this week. Okay. All right, so that's the plan going forward, guys. Okay.